Hello everyone. In today's video, I'm going to introduce a concept known as the Betz limit in wind turbine analysis. So starting with what is it? The Betz limit is a well-known maximum on the power that can be extracted by a wind turbine immersed in an unbounded free stream flow. And as the name suggests, this is a limit that was derived by a researcher named Betz, who is a German researcher. Less known is the fact that it was also independently derived around the same time, 2 other times. And those 2 other scientists, one was an English researcher, or a researcher in England named Lanchester. Another was a Russian named Joukowsky. And as you can see, Betz did his derivation in 1920. Lanchester is credited with doing it in 1915, Joukowsky around the same time as Betz in 1920. So these are all representatives of 3 different aerodynamic schools that were developing in parallel at this time in sort of the golden age of classical aerodynamics. We had the English, the Germans, and the Russians all developing much of the same theory at the same time in parallel. And if you're interested in some of that history, I would recommend reading this paper that I've cited right here by Van Quick in 2007. So he calls this limit the Lanchester-Betz-Joukowsky limit. He says that should be its full name to give credit to all 3 of these independent developers of the theory. But of course, in common parlance for convenience, I'm going to stick to the convention of calling it simply the Betz limit. But this video today is not about the history of aerodynamics or about this particular concept, but rather how do we derive it. So if you're a student in an undergraduate fluid mechanics course, it is possible you already have the tools necessary. So the nice thing, and what makes this a great example, even just for teaching, is that it doesn't require an advanced set of mathematical tools. So the tools we're going to use are control volume analysis. So I will assume that you are already familiar with how to do a control volume analysis, specifically a static control volume analysis, which is the simplest kind. And on a control volume, we're going to need to apply 3 conservation laws: the conservation of mass, the conservation of momentum, and the conservation of kinetic energy. So let me just move these historical notes out of the way. And now let's consider the problem at hand. So I've drawn over here a turbine rotor, which when rotating is going to sweep a circular area, which I've now highlighted here in yellow. And once again, we're considering the case that we have an unbounded flow and a steady free stream velocity incident normal to that swept disk. Now, to do any further analysis, I'm going to need to define a control volume which encompasses this body. So I'm going to draw a control volume as follows. And I will call that volume V, and I will call the outer surface encompassing it S. All around on S, we are going to have an outward facing normal vector N. And this shape that I've chosen is actually very deliberate. So if we have a turbine that's operating and extracting energy from the flow, it's going to be generating some amount of drag, and that drag is going to cause the fluid moving through it to expand. So we have an expanding wake, and this control volume is defined such that it is aligned with a mean stream tube. Specifically, the lateral boundary of this control volume is aligned with the mean stream tube, and then we have an upstream face and a downstream face, which are circular and oriented in the same direction as the free stream flow, so oriented normal to that flow. What this means is that there is no flow across the stream tube by definition, and we only need to consider the flux of momentum or mass across the upstream and downstream faces. The cost of this is by drawing the control volume this way, we don't know the area, the size of the upstream and downstream faces at the beginning. We need to figure that out in the analysis. Now, the way we're going to be able to do that is by invoking the conservation of mass. And I'm going to make a note of one of the first assumptions I'm making. It is going to simplify the analysis to assume that the flow is incompressible, meaning that the density of the fluid everywhere inside the control volume is constant. And with that assumption, the conservation of mass is expressed in integral form as this closed surface integral over S of the normal vector dot product with the velocity. That is the total flux of mass moving outside or moving across the boundary is 0. The more general equation would include a term showing the time derivative of density, but once again, this can be shown to vanish, or rather it does vanish under our assumption of incompressible flow. So we'll stick with this simplified version of the conservation of mass, and we will simplify it yet even further. We are going to assume that the velocity varies only with the axial position. That is, the vector velocity is a function of x only, where x is the streamwise direction here. This means that the velocity is constant on the upstream and downstream faces, and so this integral is going to become simpler. It's going to become simply an algebraic expression. So we can divide up this control surface S into 3 separate surfaces. So we have the upstream face, which I will call SU. Then we have the downstream face, which I will call SD. And of course, we have the lateral boundary, which I will call SL. With those definitions made, this integral can be expressed as the sum of integrals over those 3 components, like so. Now, this is where our control volume definition and its convenience become obvious, because by defining SL as being lying on a mean streamline, what we can say is that n dot u is equal to 0 everywhere on SL, because that is what it means for it to be a stream tube. So if you're not familiar with this notation of scalar products, what I'm saying is that the component of the velocity in the direction of n, that is, crossing the stream tube, is 0 by definition. So this allows us to simply ignore that last integral. We have also defined our control volume such that the upstream face is well upstream, away from any disturbance generated by the presence of the turbine. So that means that n dot u equals negative u infinity on SU. And the negative sign comes from the fact that n, as drawn up here on the top left, is in the opposite direction as the velocity vector in the free stream. Let me just move this up so I can make room for our last statement, which is that n dot u is equal to some constant but as yet unknown velocity uw on SD. Now, when we substitute these relations into the integrals, we just have the integral of a constant value over these 2 areas, and so this reduces to an algebraic expression because these constants can be moved outside the integral. So what we have is this relationship here. Now, AU I'm defining as the area of the upstream face SU. So the distinction between SU and AU is that SU is referring to a surface, AU is the area of that surface, and likewise AD is the area of SD. Rearranging, I get this relationship here, and I can relate this to yet one further product of a velocity and an area, and that is the velocity at the rotor itself multiplied by the area, again, of the rotor itself, AR. This arises because if I go back to this picture here, there's no reason I couldn't have done the same analysis and come to the same conclusion, but moving that downstream face right up to the turbine. So this is true on any plane intersecting that control volume that we've drawn. So this relationship here, these three products that are equal, are going to be necessary coming up. Now, as I mentioned, we still don't know what UW is, so we're going to need to invoke another conservation law so that we have more equations with which we can solve. Now, the expansion of that wake is going to be related in some way to the force that the rotor is applying to the fluid. So the next logical conservation law to invoke is the conservation of linear momentum, which in integral form, and using the same control volume definition as before, is expressed as, here we have F being the vector force that is applied by the fluid on the turbine, and then the first integral here, this time derivative, is the rate of change of momentum inside the control volume. And again, density rho is outside of the integral because I've assumed it to be constant, so I can put it there. And the second term is the flux of linear momentum leaving the control volume. Now we simplify this further by invoking another assumption, which we have not explicitly stated yet. So this first integral is going to vanish under the assumption of steady flow inside V. Now, obviously, if you're following a fluid particle as it moves through the volume, its velocity is changing, so this may seem confusing at first, but what we are saying is that at any given point in space, at any given time, the velocity is the same as at all other times. So velocity changes with space, with the spatial variables, but it does not change with time, and therefore the time derivative of this integral will vanish. Over here in the flux term, on the second term on the right-hand side, we have again this scalar product of n and u, and we've already established what this product is equal to on the three components of S, on the SU, SD, and SL. So we can write F as, and we can make this even a little bit simpler yet. I'm still expressing F here as a vector quantity, but we're only going to be interested for this analysis in the axial, that is the x component of the force. And so we can divide out the components of the velocity. And so we're only interested in the x component, and we get, and this expression simplifies again to an algebraic expression, because we can take these values, which are constant on their respective surfaces, move them outside the integral, and at last we get the nice simple expression shown here. Now it will prove convenient because we still have in this expression now, we actually have three different unknowns that we need to deal with, but we can simplify this expression by invoking the conservation of mass as we just derived it. So scrolling back up, we're going to take this expression and substitute it in so that we get this expression here. So just to clarify, what we've done is this URAR is equal to both UWSD and U infinity AU. Sorry, allow me to be consistent. That should be AD. And in this expression, we now have only one unknown because we know the area of the rotor if we know the geometry of our turbine. Oh, sorry, we have two unknowns still. Scratch that. The wake velocity and the velocity at the rotor. But we'll get to how this becomes convenient. Now, I want to pause for a moment so as not to get lost in what we're doing. So let's go back to our goal for a brief moment. Our goal is to derive the maximum power that can be extracted by a wind turbine in a steady free stream flow. And so far we've only looked at momentum and mass. But of course, power is just the rate of change of energy. So we are going to, at some point, need to introduce the conservation of energy. So we're going to do that now. Before we write out an expression, though, we need to discuss what are the types of energy that are present in this flow. So of course we have a moving flow, we have kinetic energy. If you think back to any of your work in thermodynamics, you'll know that there's also enthalpy or internal energy, and that would be related to the pressure as well as the temperature. Now, because we are looking at an incompressible flow and an isothermal flow, so we're not going to consider temperature whatsoever. The only energy that actually is consequential in this analysis is kinetic energy. You will recall from rigid body dynamics that the kinetic energy is 1/2 mu squared, where m is the mass of the body. So now if we're looking at this on a per unit volume basis, we're going to have each fluid element having a differential amount of kinetic energy equal to 1/2 rho u squared. Applying that to the control volume, and of course you can express any conservation principle for control volume by invoking the Reynolds transport theorem. I won't show that explicitly, but I want to make that reference if you want to review that theorem. We have the time rate of change of energy in the control volume, or its negative rather, being equal to the useful power extracted from the volume, and that is equal to, now once again we have an unsteady term, this first integral here, and we have a flux term, which represents the flux of kinetic energy across the boundary. And invoking the assumptions we've already made previously, this first term vanishes by the steady flow assumption, and I'm going to move these densities outside of the integrals. Of course, the first one doesn't matter. And again, I know n dot u on the three components of S, which I'll rewrite here briefly. And so we get power being equal to this first integral involving u infinity cubed and the second integral involving the wake velocity cubed. Again, these velocities come outside because they are constant, and our power expression collapses to something algebraic. And invoking conservation of mass as before, we get this expression here. And just to quickly avoid confusion again, as before, I'll remind you that this UR/AR by conservation of mass is equal to either of these two expressions. We now have three equations, which I've derived in box as being somehow special. So let me rewrite those three together, and we'll take a look at them. So I'll just scroll down, and here they are. So scrolling down, I have the three equations here. Let me zoom in again on the power equation and note that we still have two unknowns. Now for our goal, we actually only need to get this down to one unknown, because of course the turbine can vary in operation, so there has to be one degree of freedom, one variable that is free to change, and then we need to determine what value of that variable gives the maximum power. So what we're going to try to do here is express this equation here in terms of, express this power in terms of one or the other of UR or UW. Now the way we're going to do that is to relate the power to the force in two different ways. So firstly, we can see, just comparing the second two equations here and invoking the binomial theorem, which in this specific case gives us this difference of squares being equal to this product here on the right hand side. And from that we get power being equal to 1/2 times fx times u infinity plus uw. Now this isn't particularly familiar. What would be more familiar would be an expression that looks like power being equal to a force times a velocity. And so we're going to assume that the fluid passing through the rotor is all doing useful work on the rotor. And so we're also going to express power as being equal to the product of Fx and the velocity at the rotor, UR. Of course, power is power, so these two expressions must be equal. And from this we get UR as being equal to 1/2 u infinity plus uw. That is, UR is the average of the free stream and the wake velocities. Now this is crucial to being able to come to our conclusion. I'm also going to rewrite that as uw equals 2ur minus u infinity. And this expression I'm going to sub back into our original expression for power that we got from conservation of energy. So that gives us, well, first we have our original expression, which we expanded. Now this 1/2 and this sum here is going to give us UR by the original relationship that I just underlined up here. So we have this expression here where I've substituted in the expression for UW. And now, at last, we have an equation with only one unknown, which is UR, because AR is known and U infinity is known. And this simplifies to this expression. Now, before we go looking for the maximum in this equation, we can note very briefly where the maximum is not. So consider the case where UR is equal to the free stream. That is, the turbine represents no obstruction to the flow. So the flow going through the turbine area is equal to the free stream. But of course, if UR equals U infinity, then the terms in brackets cancel and the power is 0. So when there's no obstruction, there's no power extracted. Of course, at the other extreme, if the turbine represents too much of an obstruction, we're trying to extract all of the kinetic energy in the flow and decelerate its velocity to 0. Well, if UR is 0, then once again, now this is just a plate, a non-porous plate in the flow, and that does not extract any energy from the flow. So there's an optimum velocity at the rotor for extracting the most possible power. Now to find a maximum, as we know from our calculus studies, we're just going to take the derivative of P with respect to UR and set it equal to 0. So this is the case at UR optimum. And when I take that derivative, which I won't show, I'll just show the result, we get rho AR UR times 4 u infinity minus 6 ur. Now, this equation is satisfied if ur is equal to 0, but as we just discussed, if ur is equal to 0, this is not an optimum. We do not have a maximum power, so this would be some sort of local minimum. But getting the terms in brackets to cancel, we have ur being 2/3 the free stream velocity. And I should, to be consistent, call this ur opt. So the optimal velocity is 2/3 that of the free stream. When we substitute that back in to this equation here, we get the optimal power that occurs at that optimal velocity. And from that we get optimal power being equal to 8/27 rho AR u infinity cubed. Now, it's important to note here that we have a dependence on u infinity cubed. So think about that just for a moment. That a wind turbine's power operation, its optimal power that it can extract from the wind, is dependent on u infinity cubed. So a doubling of the free stream velocity increases your possible energy extraction by 8 times, 2 to the 3. So this is very important to note, that wind turbine operation is highly sensitive to the free stream velocity. Now, to finish up, I'm going to express this as a power coefficient, which is the way that the Betz limit is typically expressed. So Cp is the power coefficient, and is defined as power over 1/2 rho AR u infinity cubed. So our optimal Cp opt is equal to 16/27, which is approximately 59.3%. And this is usually what you will see when you hear someone refer to the Betz limit. Now, to wrap up, I just want to recap the assumptions we've made to come to this result, so that we know the conditions under which the Betz limit does not apply and which efficiencies can reasonably be expected to exceed this limit. So, what were those assumptions? Firstly, we assumed the flow was incompressible, so our rho is treated as density throughout the control volume. We assumed that the velocity only varied with axial position. Now, this will become especially important because the velocity behind the rotor will actually have an azimuthal component, because the flow is generating a torque on the rotating rotor. And so that extra component of velocity is going to change the flux of kinetic energy, leaving out the downstream plane. So as it turns out, this limit is somewhat conservatively high. So for a real turbine in which there is some swirl in the wake, the limit will be somewhat lower. But this limit then still serves as an upper limit, and therefore is useful in a sense of giving us a ceiling. We also assumed that the flow was steady, meaning that at a given position, the velocity never changed with time within our control volume. And we assumed that the power could be expressed in this work sort of relationship, that the force times the velocity at the rotor is equal to the power extracted. So this is tantamount to assuming that all of the force is associated with useful work being done. Of course, a force can be generated on a body without any useful work being done, but we are assuming that all of the force is related to useful work. And lastly, although actually firstly, we assumed that the flow was unbounded. Now this becomes important because there are ducted or shrouded turbine designs where we have some sort of profiled diffuser that is directing more fluid through the rotor. In this case, if we define the power coefficient based on the rotor area, as I've done here, it will be possible. or at least hasn't been definitively proven to be impossible to exceed the Betz limit. Or no, I should say, with this definition by the rotor area, it certainly can exceed the Betz limit. We might define it based on some total frontal area of the system, but I don't want to get into that detail here today. But if you have a ducted system, the Betz limit, as defined, may not apply. One other trick I'll warn you about that I've seen with people having novel turbine prototypes is they may express the efficiency as a ratio of the power coefficient divided by the Betz limit. And so then they might report an efficiency of 90%. Of course, for marketing purposes, that sounds better. But when you hear such a number, remember that that can only be true based on a convenient definition of the power coefficient or the efficiency, or if one of these assumptions I've listed has somehow been violated. And with that, I think I will end this video here. If you have comments or questions, please leave them below. And thank you for the view.